Thanks for joining me today for episode 724 of People Behind the Science. I'm your host, Dr. Marie McNeely, and today we are revisiting our conversation with our guest, Dr. Ellen Arruda, originally released on November 6th of 2017. Listeners, Ellen's work spans the fields of mechanical engineering, bioengineering, and materials science. Her lab studies soft tissue biomechanics and polymer mechanics with the goal of understanding and characterizing the mechanical properties of a wide variety of materials using both experimental and computational techniques. And in her interview, Ellen shares some outstanding stories and insights about her life in science. So sit back, relax, and enjoy this episode of People Behind the Science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of People Behind the Science. Today, I am looking forward to introducing you all to Dr. Ellen Arruda. So, Ellen, thank you so much for joining us on the show. How are you?
I am well. Thank you.
Wonderful. We are excited to learn more about you and your work today, but I want to start by introducing you to our listeners. So listeners, Ellen is the Maria Comninou Collegiate Professor of Mechanical Engineering with joint appointments as Professor of Biomedical Engineering, as well as Macromolecular Science and Engineering at the University of Michigan. She received her bachelor's with honors in engineering science and her master's in engineering mechanics from Pennsylvania State University. Ellen was awarded her Ph.D. in mechanical engineering from the Massachusetts Institute of Technology, and she joined the faculty there at the University of Michigan afterwards in 1992. Now, Ellen has received numerous awards and honors for her outstanding research, teaching, and service, including the Ann Arbor Spark Best of Boot Camp Award, the Excellence in Research Award from the American Orthopaedic Society for Sports Medicine, the Ted Kennedy Family Team Excellence Award from the University of Michigan College of Engineering, the Research Excellence Award from the College of Engineering at the University of Michigan, the Cadell Memorial Award, the Outstanding Engineering Alumnus Award from Pennsylvania State University, the Distinguished Faculty Achievement Award from the University of Michigan, as well as the Trudy Huebner Service Excellence Award from the College of Engineering at the University of Michigan. Now, Ellen is also a Fellow of the American Society of Mechanical Engineers, the American Academy of Mechanics, and the Society of Engineering Science. She was also named a Centennial Fellow of the Department of Engineering Science and Mechanics at Pennsylvania State University. And recently, Ellen was named a member of the National Academy of Engineering. And listeners, Ellen is here with us today to talk about her experiences in life and science and engineering. So Ellen, today we want to get to know you both as a scientist and as a person. So can you start by telling us what you like to do with your time when you're not doing science?
I like to run. That's my favorite form of exercise and a good time for me to think through ideas. I get a lot of good ideas when I'm out running on a beautiful day like it is here today in Ann Arbor. Mm-hmm. I love to cook. And when I have time, I do knit, but it's harder to find time for that.
Gotcha. So you mentioned all these things that I've sort of tried to do and never been able to get into, but I love it. Running, cooking, and knitting. So tell us, what do you like to cook?
Everything.
Yeah.
My husband and I both love to cook, and we love all types of food. So we try everything that sounds like it would be good.
Absolutely. And knitting, I will say I've got a couple lumpy scarves in my collection. What's your specialty?
Sweaters.
Yeah? I've never done anything more complex than a scarf. It's a little bit intimidating. How'd you get into knitting?
Well, when I was younger, I crocheted, actually, because my mother crocheted. And I always wanted to learn how to knit. And I would try to teach myself because I didn't have anyone who knew how to do it. Mm-hmm. But I'm left-handed, and all of the books describe knitting for right-handed people. So instead of biting the bullet and trying to knit right-handed, I was trying to reverse it and figure it out.
That'd be a nightmare.
Yeah, with limited success. But then my mother-in-law knits, and she's a beautiful knitter. And so I just sat and watched her one day and figured it out.
Very cool. Well, great to get a window into how you spend your time when you're not hard at work. But Ellen, I do want to talk about your work next. So can you tell us how you describe your work to someone who's not at all familiar with you or your field?
It depends on whom I'm speaking. I often have to explain what I'm doing to people at different age levels, including children and then high school kids, college kids, then people outside of science who are adults. And I think my approach is one of a question and answer so that I can relate to them what they do and don't understand or know about science, and try to use examples that they can relate to.
I like that you make it more of a dialogue, because I think we often dread when you ask someone what they do and they go off on this 10-minute tirade and eyes glaze over.
Right. And then you just don't know if you're making any sense at all. So if they're going to take the time to ask the question, I'm going to really try and make sure I give them an answer that is helpful.
Yeah. So if a student, let's say, for example, at the undergraduate level were to approach you and say, can you tell me about your work? What would you say?
Sometimes with a student at the undergrad level, I might say, well, what's your major? Have you taken classes in XYZ? And then I'll relate it to classes that they may have had. A lot of times when I'm speaking with students, I can just walk them over to the lab across the hall from my office and show them. So that experiential learning aspect of it.
And I know you do some really cool work with different materials and polymers and soft tissues and things. So how do you describe this kind of work in general, if you had to do it in like a sentence or two?
In general, I study the mechanical behavior of soft materials like polymers or plastics, but also like the soft tissues of the body. And we're trying to understand, in some cases, how to design with them so that they won't break when we use them in that design, or how to design something to replace them if they do break. As in, if you tear your anterior cruciate ligament and need to have it replaced, can we design a better replacement than what is currently out there?
Very cool. Well, Ellen, I'm looking forward to chatting more about your research projects as we go through our call today. But I do want to chat a little bit about motivation first. I think there are so many different motivational forces that keep scientists going in every day and doing the amazing work they're doing. So do you have a favorite quote or a saying or a force that really keeps you moving?
I actually have two. One is, you must do the things you think you cannot do, Eleanor Roosevelt. And another is, whether you think you can or think you can't, you're right. And that was Henry Ford.
I like both of these quotes.
They both just sort of speak to your mindset. The Henry Ford quote is great. If you're really going to set yourself up for failure, you're going to fail. So that's just not a viable approach to success. And Eleanor Roosevelt's quote is more when I'm thinking about stretch goals for something and going for something that's harder to attain. In our world, there's a lot of competition for grant money and getting papers published and things like that. So when I think about meeting that stretch goal, that's a quote that comes back.
I like it. Well, I think in science and engineering in general right now, we're pushing so many of these boundaries. You are doing the things that you think you can't do, right? It's like every day in science and engineering. So
it's true. That is the role of the engineer, is to solve problems in society, solve problems that are out there by discovering new ways to do things or new tools or methods or putting existing approaches together in a new way.
Absolutely. So for you throughout your career, did you have particular people who you really looked up to or who inspired you along your path?
Sure. I'd say the first engineer who inspired me is my older sister, Julianne. Mm-hmm. She's a year older than me, and she sort of paved the way for me. She's an architectural engineer. And I've just admired her strength and confidence the entire time she was going through engineering. Even though I was just a year behind her, I just thought, well, she can do it. I can do it.
I like it. And who was the second?
The second was my undergraduate and master's thesis advisor, Dr. Richard Queenie from the Pennsylvania State University. Mm-hmm. I had to do research as an undergrad for my honors thesis, and I chose to work with him. And he was just a very supportive mentor.
Excellent. So have you taken bits of what you've learned from Professor Queenie then and incorporated it into how you mentor students today?
Yes, I think I've taken bits of various academic mentors along the way and incorporated them. But he was probably the first person who said, sure, you can do this research project, right? And set me up in front of this huge machine and said, go for it.
That's awesome.
Thanks.
So now, Ellen, you mentioned that you have an older sister who had an interest in engineering as well. Mm-hmm. Can you recall the earliest point in your life when you kind of started getting interested in engineering or maybe started thinking about this as a potential career?
So it really wasn't until college. I knew that I wanted to go to college. I didn't know what I wanted to major in, and I didn't know a lot about what engineers did, except that my sister was majoring in engineering. So I explored all of the options available to me at Penn State, and Penn State's a huge place, so there were lots of options.
Yeah.
And I sat down and essentially read the book called the Blue Book of all the majors that they had at the time. And I thought engineering looks interesting, but I don't know what kind of engineer I might want to be. And that's when I chose engineering science, which at the time was the only honors major on campus, but it was a bit of a mixture of the traditional engineering fields that we tend to think about: mechanical, electrical, material science, and engineering. So I got a little bit of all of that, and it really gave me a chance to think about what I'm most interested in. And then being able to do research really solidified my path for me. I found that I really enjoyed doing the research and wanted to continue. So I continued on for a master's degree and changed the research topic somewhat, but still loved it. And then said, okay, this is really what I want to do. And I can love this job, actually.
Yeah.
When I realized I could have a career doing research and it's something I love, that was it.
All the pieces fell into place.
Yeah.
Now, you mentioned you had this moment where Professor Queenie sat you down in front of this big, scary looking machine and said, go. I think this hands-on experience can be a little bit daunting for people the first time they're kind of thrust into it. So what was that experience like for you?
It is daunting. And I had all of the information in front of me, and I had to just make it work, basically. So I made sure I was very, very careful, followed directions very meticulously, and went slowly and built off each success. So turn the machine on. Yes, it turned on. Okay.
Flashing light, go.
Nothing exploded. And I started doing small tests of the equipment and learning how it worked and what to do and what not to do, and built up from there until I was finally doing these experiments that defined my undergraduate thesis.
Certainly. And then we mentioned you went on and did your Ph.D. at MIT. What was your experience like there?
I loved it. I loved MIT. My PhD advisor, Dr. Mary Boyce, was wonderful. She's now Dean of Engineering at Columbia University, but I was her first PhD student at MIT.
Oh, cool.
We had a wonderful working relationship, and I just learned so much there. And as a PhD student, a lot of times your success and happiness is a strong function of your research laboratory environment. And mine was great. Great friends from there, colleagues who were also PhD students at the time, also made it a great experience.
Absolutely. I couldn't agree more. I think students out there, if I could give them any advice, it's choose the lab that you're going to work in wisely, because
I tell students the very same thing.
Yeah. The correlation between success and a good lab environment is very strong, I think.
Yes.
So now you ended up joining the faculty then at the University of Michigan. Can you tell us what drew you to Michigan?
A couple things. One, it is very similar to Penn State, both large state schools in a relatively small town, although Ann Arbor is quite a bit bigger than State College, Pennsylvania. So it felt like a campus that I was familiar with. And it has, in addition to an excellent engineering school, it has several other schools and colleges that are outstanding. And so although I wasn't fully appreciative of it at the time, the potential for collaborating with people outside of engineering was tremendous. And over the years, I've established collaborations with a number of people, many of whom are in the med school. So those were the main draws at the time.
Excellent. So can you tell us, Ellen, about a project that you're working on right now there at the University of Michigan that you are just really excited to be a part of?
So one of the projects I'm working on with my team here is on the design of a sports helmet that would do a better job at mitigating injury to the brain than the current helmets. So we've been looking at this problem for a couple of years now, and I can tell you that modern sports helmet really was designed to prevent skull fracture, which is a very bad thing. We can all agree. The helmets prior to the modern helmet were those leather caps that you've seen probably in pictures. And they didn't protect the skull, and skull fracture was a real potential outcome. So current helmets do a really good job at that, and that's good. That's great. It's only more recently that we've learned about brain injury that has caused us to take a closer look at how we protect the brain as well. That's what we've been working on for a couple of years now.
So what are some of the differences or maybe changes that you're looking at making in helmets to make them a little bit more protective of the brain?
One of the things helmets do well is a helmet takes the force of an impact and lowers it. By lowering that force, you lower the force that hits the skull, and that's how it protects the skull, and you lower the force that gets transmitted into the brain, which under certain circumstances helps prevent brain injury too. But that's not the only thing you need to do to protect the brain. Even if you lower the force, the impact event itself has energy associated with it. It has momentum. And the laws of physics say that momentum has to either be conserved or removed through dissipation. And that's the part that has not been optimized in current helmets in our findings. We believe that we can design helmets with combinations of materials that will do a better job at both reducing the force and dissipating momentum. Both of those are important in impacts. One is important in certain impacts, the other is important in other impacts. And so a helmet needs to be designed to do both.
Very cool. And I could see how this could quickly become a very interdisciplinary kind of project. So are there other groups that you're working with on this?
Well, this work has been largely with a bunch of mechanical engineers. So to your point, there's a lot of related science. One is the science of brain injury itself. What specifically happens? What is the mechanism at the level of neurons and axons in the brain that causes damage? And that is still an open question. The neuroscientists are trying to understand that. The other issue is around how helmets are tested. So if you don't really know exactly what causes damage to the brain, how do you know what you should be testing the helmet to do?
Right.
So there were people working in that area too. Some mechanical engineers, some people in kinesiology, which is a study of movement science, for instance. But our approach has been, even though we don't know precisely what the mechanism is at the brain cell level, we do know from physics that if you minimize everything that could potentially cause harm in an impact, you will make a safer helmet.
Absolutely. And are you thinking primarily about, say, a football helmet, or are there other sports that you're considering?
The approach is valid for a number of sport helmets: hockey, lacrosse, and football. And also even in activities in which the helmets don't necessarily have to be worn. I think when you skateboard, you don't necessarily need to wear a helmet or are required to wear a helmet.
I was thinking cycling and stuff too, yeah.
Cycling too, but the bicycle helmet has another mechanism of dissipation available to it, and that is that it breaks. When you fall off your bike and have a serious enough hit to the helmet, it breaks, and that dissipates energy. That's a strategy, but it's a difficult, impractical strategy in a football game. You can't simply stop after every play and replace everybody's helmets if they broke.
Exactly.
It's incredibly costly.
Mm-hmm.
So ideally, a strategy that doesn't require replacing the helmet after every serious hit is
pretty desirable. Yeah.
Mm-hmm. Yep.
Well, Ellen, great to hear about one of these projects that you have working on in the lab. And I think so far we've talked about a lot of the great aspects of your career and how you got to where you are today. But Ellen, I know there are so many challenges and roadblocks along the way. So is there a particular challenge or a failure that you faced in your life that you really struggled with that you can tell us about today and how you worked through it?
Well, there are many struggles in academia. Mm-hmm. Every rejection is a struggle. And there can be a lot of rejection. Proposals get rejected, papers get rejected. And oftentimes you get the feedback And your initial reaction is to get very, very frustrated by it because you don't think the person's feedback is accurate or
it's not fair. Yeah.
Whatever. And the way I work through that is a long time ago, I sort of realized that if I'm getting feedback that isn't matching what I intended to say, I have a role in that communication breakdown. And I have to recognize that not being clear or precise in my language use on my end is part of the problem. So it softens the blow sometimes to say, all right, where should I have been clearer? Where did I fall down? And it's incredible how after a proposal or a paper has left your desk and you sit down and read it a few months later with sort of fresh eyes, you find things that you've said in there and that you could have said so much more precisely or accurately or clearly. I think that's been a helpful realization that it's easy to blame the reviewer. The reviewer is an idiot, but
most of the time they're not. They're smart people. Yeah.
And most of the time they're trying to do the right thing with the information they have.
Absolutely. Well, Ellen, I really like to hear how you approach this in terms of taking responsibility for it. And I think that gives you a sense of control because in a lot of these application processes, it almost feels like a lottery for a lot of people. They don't necessarily feel like they have control of the outcome because in some cases, it really depends on who your reviewers are. It depends on what they're looking for. But I think bringing that locus of control back to you and really saying, okay, what could I have done better? How could I have described this and sold it better? Makes you confident that you can go on and do better next time.
Exactly.
So is there a particular, maybe recent or maybe a particularly painful one of these rejections that you can recall?
Well, my first big rejection was the first time I wrote a proposal to the National Science Foundation's career program. So this is a program young faculty write to, and my proposal wasn't selected the first time. And part of the feedback was that I obviously knew nothing about the dogma in engineering education. And I thought to myself, that's absolutely right. I don't. Right. I was hired because of my research, and it's expected that I can teach, but nobody quizzed me on my teaching strategy or anything like that.
Sure.
And I remember I told my former Ph.D. advisor about that at the time, Mary Boyce. I was visiting her, and she pulled a book down from her shelf on engineering education and threw it at me.
Really?
And said, Ellen, read this. So it's a good example of what I just said, that you have to own your responsibility in the negative reviews. And the next time around, prior to writing the proposal, I sat down and read this book and got a much more coherent idea of what I can talk about on the education side of the proposal. And I got the grant.
Oh, congratulations.
Yeah,
I like stories with a happy ending. Yeah. Well, that sounds like a wonderful challenge that you learned from. In this case, not getting the award the first time, but being able to take that feedback, do something constructive with it, and submit a stronger proposal the next time. Well, I love talking about happy endings, Ellen. So I do want to talk about successes next. So can you share one of your own successes, whether it was a big win or a small victory, one that was particularly meaningful for you?
It's always nice to win awards, but I'll point to a recent one. So this research on helmets, we were named a finalist in this national competition, the Head Health Challenge. It was the first time we felt our approach, which was very much a mechanics approach, was actually resonating with somebody. That somebody finally understood that what we're trying to do is important and can make a difference. So we were very, very happy that we were named one of the finalists in that competition.
Well, congratulations. So what was going through your mind when you heard the news?
Just that we might be able to make a difference. With that award came some funding so that we could pursue our idea and potentially come up with a prototype that would work better. So the goal in a lot of our research, even though sometimes it's not obvious to the public, but what we're trying to do is help society, help people solve problems that the world is facing to make challenges less challenging. And a lot of times it seems like we're really disconnected from that, but we're doing the basic science that would lead to changing the world for the better. And this is a case in which it's a lot more clear. The path to application is quite clear.
Right, right.
We want to work on impact mitigation in helmets so that we can make a better helmet, a safer helmet.
And now you're taking it too from this very basic laboratory-based science too. You mentioned the potential for prototyping and creating samples of these helmets that incorporate your findings and technology. So what's that experience been like?
It's rewarding and it's sometimes frustratingly slow. Mm-hmm. But we are talking with helmet OEMs, helmet manufacturers, and material suppliers, and trying to find a way to work together to build a prototype. I don't want to start my own helmet manufacturing company.
Right.
But if I can work with an existing helmet manufacturer and convince that company that there's a way we can help, and also there's a way we can get the materials we need to do what we're trying to do, then first of all, we can get to market faster with strategic partners who do this, and we can help some people sooner, provide safer helmets more quickly.
Absolutely. So are you finding that the manufacturers, these groups that you're working with, are pretty open to incorporating your suggestions, or has it been a little bit challenging to maybe even get on the same page in terms of the language and then to start moving from there?
I think there was just a little bit of a give and take in terms of what are all of the challenges, what are the boundary conditions you're facing, we're facing. Do I understand all the constraints around being able to manufacture a helmet and get it certified? Initially, I didn't. So I needed to understand what the helmet manufacturer goes through, and they needed to understand what we do here in a research enterprise.
Sure.
But I'm finding that working with them is more rewarding than not because we all have the same goal. The helmet manufacturers certainly want to make safer helmets.
Absolutely. Well, congratulations again on the success being named a finalist in this national competition. And we've chatted about your life outside of science just a bit, Ellen. And I love talking to scientists about what they are reading because I love adding books to my recommendation list. So, Ellen, do you have a favorite book that you'd like to recommend for us today?
One of my all-time favorite books, if not the all-time favorite, is Watership Down by Adams. The story of a group of rabbits that had to leave their warren and find a new place to live. I like to tell people that what I understand about leadership I learned from that book, because the leader of that group was Hazel. And Hazel wasn't the smartest bunny or the fastest bunny or the most intuitive or the strongest, but he understood where the strengths were in his team and he played to those strengths.
I like it. So are you a pretty avid reader then?
When I have time, I love to read. When I was a teenager, I just read the classics. Mm-hmm. Anything anybody told me was a classic, I read it. Now I don't have as much time to read, so I tend to get recommendations from a number of sources, buy a couple more books than I could possibly read in the time I have, and get through some of them.
That's why I think my list is becoming overwhelming as I get 2 or 3 recommendations from everyone I talk to. So
yeah.
Very cool. Well, Ellen, we will absolutely add this to our online list of book recommendations for our listeners.
Has nobody ever come up with that one before?
You are the first to mention it, actually.
Oh, I love it.
It's going on my list. I have not read it yet, but I've heard of it, so I'm putting it on there.
Okay.
So we've chatted about some different aspects of your career, and I think one of the great aspects of careers in science and engineering that people don't necessarily hear about are some of the opportunities to travel, whether it's to work with collaborators, to do field work, to go to conferences. I think this is a great opportunity for people to see the world. So, Ellen, do you have a favorite place that your work has taken you?
No, because every trip is a new adventure. It's great to see new lands and experience new cultures. And like I said, I love to eat, so trying new foods. Mm-hmm. I just visited Hong Kong for the first time, and the food was amazing. The dim sum was delicious.
So what was the occasion to go to Hong Kong?
It was a research conference, and part of the thing that's really nice about the jobs we have is that when we do travel, there's usually an opportunity to stretch the travel out a little bit and go see some of the places you go to. Sometimes, though, I've traveled to a town and not gotten out of the hotel room.
Right.
But when there's a chance to go experience the culture and meet the people and see the town or the city, it's really fun.
Yeah. So were you able to block any time off to see some of the sites in Hong Kong?
Well, this was a type of conference that had talks in the morning, talks in the evening, and a break in the afternoon.
Okay.
And it would just be about a 3-hour break, but there was time in the afternoon to go on different excursions. The downside was it was July in Hong Kong and it was very hot and humid.
Gotcha.
But we still did. We went on a few excursions, went on a boat tour of the bay. It was very beautiful. Went to see the skyline at night. Also really beautiful, and went out and ate a lot of good food.
Sounds wonderful. My kind of trip. I like eating my way through a city. Yeah. That's usually how I explore.
Best way to go.
Absolutely. Well, Ellen, wonderful to hear about some of your travel experiences in science. And I think another thing that makes science and engineering wonderful things to do as a career are the people that you get to work with. And I think there are so many stereotypes out there about what scientists or engineers are like. And we like to break those on our program by showing a different side of science and engineering and some of the funny and fun things that you guys get to do when you're together. So do you have a particular tradition or a funny memory you can share with us today?
Well, part of being in a research lab is bonding with the others in the lab and engaging in collective goofiness. When I was at Penn State, we used to goof on our advisor a bit. Again, this is Professor Rick Queenie. He was a little bit of a geeky geek nerd, but super, super nice guy. And we did things like we tie-dyed his lab coat.
Oh, really?
Yeah. And when he got his first laptop workstation, so the department told him that he needed to get a computer. They were getting all the faculty computers. So he got it and it sat there in the box. And then the department told him, no, you got to open it.
At least plug it in. Come on. Yeah.
He said, if you guys want to use this, go ahead and put it together and we'll have it for the lab and we could use it. So we set it up and he would come in the morning and he would just turn it on. And that was pretty much all he did. He didn't use it. And one day we programmed it so that when he turned it on, as it finished booting up, you heard Fred Flintstone's voice yelling, yabba dabba doo. And he just didn't know what it was at first. He's looking around trying to figure out what had happened. And then once he realized what had happened, he was always good natured about it. And in that case, pretty impressed because he had no idea you could program the computer to make a noise. Yeah. Other than that whirring noise it makes when the disk is spinning up.
That's awesome. So how did the tie-dyed lab coat come out? Did it look good?
It looked really good.
Excellent.
But we really took his, swapped it for an identical and tie-dyed that one.
You preserved the original, yeah.
We gave him back his original. Yeah. Just scared him one day because his lab coat was all tie-dyed.
That's awesome. Well, I think this really showcases the sense of humor, and I like that. Yeah. So in your lab today, do you still have kind of fun traditions or that sense of humor about you?
We have a lot of fun. We just laugh all the time about our own mistakes or odd things that we find going on with various research enterprise around. It's just good to find the humor in what we do and not be so serious. When you're in an experimental laboratory, it is safety first, and people absolutely don't horse around. There's dangerous equipment, and you take what you do very, very seriously. But when we're in meetings and just getting together and chatting, it's a lot more laid back. And then we sometimes do group excursions and go play. I can't remember the name of the game, but it's something that involves a mixture of bumper cars and highlight basketball.
Oh, cool.
It's got a name. I don't know what it is.
It sounds like fun in any case. Yeah.
Again, collective silliness, right?
Gotcha. Well, wonderful to hear that you still have that sense of humor, that sense of camaraderie in the lab group. I think that's so important. Again, taking the work very seriously, but not taking yourselves too seriously. So wonderful to chat about some of the wonderful things going on in your laboratory and also some of the projects that you're working on. I think this helmet project is really cool, Ellen, but I want you to dream even bigger with us today. If I took away all of the restrictions that you face, all of the barriers, things like funding, staff, technology, feasibility that are holding you back from answering any question in the world, what would you want to answer?
I think like a lot of people, I would want the answer to curing diseases that are so devastating. I would start with cancer, just eradicating cancer.
Well, I think that is a worthy cause for sure. So is there maybe an approach that you think you would want to start with, or is there a particular barrier that you think is standing in the way?
I would probably need more training in biology than I have.
Opportunities for learning.
Yeah. I actually do work in soft tissue engineering and tissue mechanics. So I have learned a great deal of biology and biomechanics over the years. This is since my Ph.D. This is learning I did as a faculty member, learning as I go. But I think the answers to these questions take a lot of collaborative science coming together to solve these problems. And many people, very talented, working very hard, are trying to do this. And if there's any way I can contribute, I'm happy to.
Certainly. Well, I love that you highlighted this idea of lifelong learning here. I think you never know where these collaborations and opportunities are going to take you down the road. And I think that's something our listeners may not appreciate is you go into a particular field, maybe it's mechanical engineering, and you may be working on biology in the future. You sort of have no idea and you just kind of go where these opportunities take you.
That's right.
So what really started, I guess, for you turning down this path of biomedical engineering?
That's a good question. I was still an assistant professor, and a student came in with an interest in looking at some soft tissue and trying to describe the mechanical properties of these materials. And they were similar in theory, but different in the sense that they're organic. And I also didn't know very much about the terminology and jargon of biology and biomechanics. But the student was interested and had some background. So we started working together, and it just went down this pathway. I got more students with additional interests in those areas, and we did more and more, and I found collaborators and so on. So I think the life of a faculty member is really one of being open to opportunities that come along. And yes, you have to pick and choose. You can't do everything, and you can't spread yourself too thinly. But in my case, I added a whole new branch to my research enterprise by being open to considering this tissue mechanics work.
Certainly. And I love this kind of piece of advice you wove in there of you're not able to say yes to everything, but do keep an open mind when some of these opportunities come along. So is there any other helpful advice you'd like to share with our listeners?
I don't know much about the demographic pool of your listeners, but if you have listeners who are thinking about careers in science and engineering, or not thinking too strongly about them, but are curious about some subject and are listening for that reason, recognize that engineering requires people with interests and capabilities that are much broader than what we often have told people in high school. It's not just you got to be good at math or good at science. We need people who think creatively and collaboratively and are passionate about solving problems. And a lot of the engineers coming into Michigan and probably other places as well carry that passion with them. There's something they want to do, and they may not know exactly the pathway to do what they want to do, but they've got something in mind, some way they want to make an impact. And they come to engineering and they find that path. So my advice is consider that even if nobody's ever told you engineering is for you, engineering could be for you.
I like it. Listeners, dig out that blue book of measures and do some reading here. Well, Ellen, wonderful advice to give our listeners. Is there any other additional piece you'd like to give them or a last note you want to leave them with?
I suppose the corollary to that is do what you love. Find your passion, find your path. It's your career, it's your life, and you're going to be waking up to get to that job at 8 o'clock in the morning every Monday for many years, in most cases. So you really want to find something that you love to do.
I like it, Ellen. Wonderful advice again. Can you tell our listeners if they want to learn more about you and the amazing work that you're doing, where should they go?
The best place is to go to my webpage. The address is my last name, ARRUDA.engine, ENGIN, UMich.edu.
Excellent. Well, listeners, definitely check out that website, read up on some of the fantastic projects going on in Ellen's lab. And Ellen, thank you so much for joining us on the show today to share a piece of your story.
Thank you very much, Marie. I really enjoyed it.
It has been a pleasure to speak with you. And listeners, wonderful to have you here as well. We'll see you next time on another episode of People Behind the Science. Your voyage to explore the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to chatting with you next time on People Behind the Science.